If you've worked through the previous episodes, you should have a basic understanding of the fundamental building blocks that go into writing a device driver for Zephyr. I realize that it has taken half of the series to get to this point, but I find that CMake, Kconfig, Devicetree, and bindings are the biggest hurdles to actually creating Zephyr projects. Even if you just plan to write applications that rely on built-in drivers, you still need to know these tools to connect it all together. And the reality is that as an embedded developer, you'll likely want to write your own device drivers at some point to do things like talk to custom sensors and control motors. With that in mind, it's time to write our own driver. In the previous episode, we looked at existing bindings files to see how they help connect the device tree to driver code. This time, we'll write our own bindings file as part of creating a custom device driver. You will want to connect two buttons to pins 4 and 5 on your ESP32 board. We'll write a simple driver that acts as a wrapper for these buttons. Later in the episode, I'll give you a challenge to write a device driver for this MCP9808 I2C temperature sensor. To create our own driver, we're first going to create an out-of-tree module. Out-of-tree means that we're not creating it in the Zephyr RTOS source code, and we're not going to fork it and version control this ourselves. Instead, we're going to make it out of this tree, and we're going to create it in our own separate modules folder that we've been working in. To create our own module, let's create a folder under there and we'll name it button. We're going to create a very simple wrapper that just turns the button code we made in episode 4 into a driver. So in that, we're going to create a drivers folder. And the naming of this is convention. If you look in Zephyr, you'll see there's also a drivers folder here, and that's where the driver code is kept. We will use CMake to point to the location of the actual driver code. We'll create another folder called button for our driver. And we're going to create our header file. We'll start off by giving it some header guards so that it can't be included twice. And yes, we're just going to rely on the drivers that exist in Zephyr, and we're just going to wrap those in our own driver so you can see how to create a driver and then write a simple application to use that driver. If you go into our button demo, into our source code, you can see that's what we're doing right here, and we're going to use most of this code. Let's go back to our header file. In many cases, you would use a predefined API that is offered by Zephyr. In this case, we're going to create our own API, which is just a collection of functions or function signatures. We're going to basically publicly expose that API and then pass it into the device tree so that we can pick it up in our application code, knowing that those are the public functions we're supposed to use for this driver. In this case, we're going to declare one function called get. We're going to pass in the device structure as well as the state. The state is an output parameter, which means that that's where the state of the button is going to go, and we're going to return one of the common Zephyr error codes to say that this function executed correctly. This is a common pattern you'll see in Zephyr. We need to declare a pointer to this function so that we can store it in this struct, and that will allow us to pass a struct with our function, so you can have more than one function in here, to the Devicetree macros that you'll see in a minute. For your challenge later, I'll have you create a driver for the MCP9808 temperature sensor that you have on your board. It's a simple I2C temperature sensor, and in fact, the driver for it already exists, and I encourage you to use what Zephyr has written as a starting point. If you come down to Zephyr drivers in sensor, you will find something that says JEDEC and then JC42. This is a common I2C interface for a lot of different temperature sensors, and the MCP9808 follows this interface. So this driver would actually work for the temperature sensor. In fact, if you want to, I encourage you to try using this driver to see if you can talk to that temperature sensor. But in an effort to learn how to create your own, what I'm going to have you do later for the challenge is take all of this and create a much more simple version of it that just reads temperature, and it doesn't use any of the triggering or interrupts that you will find in this more complex driver. But if we come to that header file, you can see where the functions are defined here. And if we go to the source code down at the bottom, you will find something that says sensor driver API. This is a struct that's defined elsewhere in Zephyr. It's considered part of the sensor package, so all of these sensors will use this common API struct, and it simply assigns functions to these struct fields. So if we go to this definition, you can see that there are a number of fields or members that it wants you to assign. These are the functions that you should create and then assign to this struct so that it is then passed into the initialization and is part of the definition for the driver when you include it, say, in your device tree, and you set up an instance of that driver. We will look at that in a moment, but understand that some of the Zephyr drivers or driver interfaces want you to use a particular API or other interface. In this case, for a sensor, it wants you to use this driver API. Another way to think about this is that the JC42 is a subclass of the sensor class, and sensor is a subclass of driver. It's just we're doing this all in C and not actual object-oriented programming. So let's close that and go back to our code. We're going to create our configuration struct so that you can set it up in your code, and this is just going to contain the things we saw in the button demo that we did in episode 4. So we definitely need that device tree spec. And I'm going to create this ID config parameter. It's going to be assigned to the instance number so that we can see how the macro expansion works later. And let me rename that to btn so it's actually spelled appropriately. And like with any good struct, I need to close it with a semicolon. Let me add a new line there, and we will save our header file. Now let's create our actual driver code. As we saw in the bindings episode, we need to create a compatible field, symbol, or string that lets Zephyr know that this is the driver code for the compatible listed in the bindings YAML file, as well as the compatible property in the device tree. So those three things must match: the compatible listing in the device tree node, the compatible listing in the YAML bindings file, and the compatible symbol found in the C code. In this case, we have to use this particular macro, dt-drv compat. The spelling of this is important because Zephyr looks for this exact macro, this exact symbol, and then looks for the symbol name next to it, in this case custom button, in order to match it to the other compatible fields found in the device tree and bindings files. Because we can't have commas in symbols, it just replaces any commas it sees with underscores, so your underscore here should match with custom comma button. We're going to create that bindings file and the node because custom comma button doesn't exist yet. So we will create all three of those, and you can see how they all work together to create a driver. The erno file just contains our error codes that we'll need in our code. We'll also include the logging header file that allows us to do driver logging, which is super helpful. It's going beyond just the print K for seeing what's going on in the drivers. And we'll include our header file that we just created. Zephyr has a fairly robust logging mechanism that's already implemented for us. And so all we need to do is register a module. In this case, we're going to call it the button module. And we're going to use this macro log module register that tells Zephyr that we want to use logging from within this code. You will see some of the macros later, but we're going to essentially log at the log default level, which is already set for us. Because of that prefix config underscore, you should already know that this is a Kconfig variable that you can go into, say, menu config and set, or set in your prj.conf if you want to, but it should be set at a default level for us. There's several levels of logging, such as info, debug, and error. Notice that we didn't declare our functions in the header file. We only created this vague notion of an API. We're going to declare our functions here. So in essence, these functions are technically private functions that shouldn't be able to be accessed by anything that includes the H file. As you will see, we will publicly expose the button state get function when we pass it into the API struct that then gets included in the expansion macros later. The button init is just for internal Zephyr use only. It lets the kernel automatically initialize our driver for us when it does its initialization routine just after boot. I like to separate my code to make it a little cleaner, so I'm going to write the private functions first. In this case, it's the button init. We'll start defining that button just as we created the signature earlier. We'll initialize a return integer. Next, we're going to get the config information that will be defined in the device tree by the user/developer. This struct device is interesting. If we go to the definition of it, you can see that there is a config, but it's a pointer to a void. So who knows what this is? This is up to the developer to figure out how to use this config thing. This could be an integer, this could be a struct, and in fact, in many cases it is a struct because it gets filled out by the device tree. And what we're going to do is we are going to cast that to our button config struct that we defined in our header file, and we're going to assume that's what gets populated here in this device pointer. So we need to cast it back to that and then store it in our config struct, or pointer to that struct that we have in this CFG variable. Next, we're going to get the button struct and instance ID from the config, and we're just going to fill out that GPIO DT spec, much like we did in episode 4. And in fact, we're not actually getting the ID here, we're just getting that button struct. However, let's log something to the console, and we're going to use this log dbg macro to log at the debug level, and we are going to say initializing the button, and we're going to give it that ID. You will see we're not going to assign this ID. Zephyr is going to automatically create an instance number, and that's what's going to get put in this ID number, and then we're going to print it so you can see which instance is being created or initialized here. Next, we're going to check that the GPIO is ready, which in other words means our button is ready. And if not, we're going to log an error, and we're going to return this no-dev return code, which basically says that there's no such device or that we couldn't initialize it. Then we're going to call the function that we saw in episode 4, GPIO pin configure DT, which just sets up the button pin as an input by passing in that GPIO input flag. If that doesn't work, we're going to log another error and return this error code. And I need to end with a semicolon as per usual. All that goes well, we will return 0 from that function. Note that this function is going to be automatically called by Zephyr, as I mentioned earlier. We will see how to set that up in a moment, but this is a private function that the user should not call. Now we're going to define our public functions. These are the ones that get passed into that API struct. That function we saw earlier, the button state to get, we're going to define that here. We're going to pass in the device structure, which should be that button/GPIO structure that we have created for us. And we're going to pass in an output parameter, which is state. We're going to fill that variable with the state of the button, either 0 or 1, and we will return an error if an error occurs, or just 0 if no error. Just like we saw in the init code, we need to get that config from that device pointer, and we're going to cast that from a void star or a void pointer to our button config struct, and we're going to get a pointer to that. Then we're going to get our button struct from that config struct. Now we can do stuff with that GPIO struct. Just as we saw in episode 4, we're going to use the GPIO pin get DT function, pass it in that GPIO DT spec struct for our button, and that's going to give us the state of that GPIO pin. Remember, we did set this up as an input. In this case, the return code could be less than 0, in which case it's an error. And if that's the case, let's go ahead and print an error message. We will also return the error to the user if they want to do something with it. Otherwise, it means the return code is 0 or 1. In that case, the state is low or inactive, or 1 if the state is active. That doesn't necessarily mean the pin is driven to ground. Remember that if we set the device tree to active low, it means that if the button is pressed, you'll get a 1 out of this. If that's the case, we will assign it to the state and return 0, meaning that nothing went wrong, and the state variable will be updated with that 0 or 1. Up until now, we've been doing mostly standard C stuff with structs, defining functions. Now we get into some wonky stuff where it's using what I like to call macro magic. You'll also hear it referred to as macrobatics in the Zephyr world. There are some fairly complex macros in Zephyr that allow us to get information from the device tree and create essentially instances of this code. We're going to be doing code generation based on device tree information or properties found in the device tree. This took me a while to wrap my head around, so I recommend going slowly through this and digging into some of the macro definitions if you'd like to learn more. The first thing we're going to do is define our public-facing API. If you remember in the header file, we declared this button API struct. and we gave it one possible field, and this is .get. And so we should assign our button state get function to this .get member. So we can go back to button.h and see that here we're declaring this API, and then we define it to have this get member, and it needs to have this particular signature. If the function doesn't have this signature, this assignment is going to fail. So if we go up to our public functions, it does have that signature, and we are good to go. So this allows you to create other functions and assign them to various members in this API struct. The naming of this API struct is fairly arbitrary. We're just going to pass that to one of these macros in a minute. Next, we're going to define our macro that generates the code so that we can have multiple instances of this driver code if we, for example, have multiple buttons. Because this is a macro, I need to write it what is essentially one line. So I'm going to be putting backslashes after every single line here. And I'm going to try to keep this as clean as possible because there is some crazy macro magic going on here. Note that I can't use the normal / to create comments because that means everything after that symbol on that line is commented out, which would mean everything else in this macro. The naming of the macro is fairly arbitrary because we're going to use a custom Zephyr thing to unroll this, or basically do a for each of the number of instances that we have run this macro. Next, we're going to create multiple instances of this button config struct that we defined in the header file. We're going to give each of these instances a name that is button config _ and a number. Note that the ## or ## when it comes to C macros means concatenate. So one instance, if we have instance number 0 or instance number 1, this is going to be button _config _0 or _1. That's going to be the name of that struct. This is going to create an instance of that struct. We are then going to fill out each of the fields in this struct. The .button field is going to be filled out with information obtained from the device tree, much like we did in episode 4. Remember that this button information we want to get is the GPIO DT spec struct. So we're going to use the macro GPIO DT spec that's defined in Zephyr for us that just gets that known struct information for us and fills out the .button fields. In order to get it from the device tree, we're going to use this DTP handle, which is a property handle, and we're going to get the instance by using the DTInst macro for this custom button. Remember that this inst parameter is going to be defined for us as part of the Zephyr build process. So that number just gets passed into the DTInst, and then we're getting that custom button instance. We're also going to get the pin number from the device tree, so that's why we're including that symbol. And GPIOs is the name of the property that we're trying to get. And that is part of this GPIO DT spec macro. You see that property is the name of the property name, and we will have created that GPIOs property in the device tree. Finally, we're going to assign that instance number to our .id so we can print that back in our initialization code so you can see how Zephyr automatically assigns this instance number for us. The other thing we need to do in this button define macro is to create a device instance from the device tree node identifier, and that's going to be a single instance of that. We're going to do that by calling this macro device DTInst define. This is a special Zephyr macro that uses that instance number to get the information from the device tree. In this case, it's unique to a device. Best way to think about it is the device class, even if it's not exactly object-oriented programming. We will pass in the instance number that will be generated for us, the button init function that the kernel needs to know what to call during the initialization process. We will also pass in these two nulls, which I will get to in a moment. You don't need to worry about them right now. And then we pass in our config struct that holds the config data for this particular instance of the driver. Notice that we are concatenating it with the inst number because we generated it earlier starting on line 89, and that's going to be the name of that struct. We're going to state that this driver needs to be initialized after the kernel is initialized, and we're going to give it the priority of the same GPIO priority that's defined in Kconfig. This is something you can set. We're just going to say, hey, whatever the priority for all the other GPIOs, let's use that as our priority too. This is predefined in Zephyr. You could set this to another level if you wanted to. And then finally, we're going to pass in our API. And remember, that's a struct that we created earlier at about line 80 that just sets the one button state get function. You can have multiple functions in here, but they need to be declared or defined in a struct that gets passed into this macro. So let's go ahead and take a look at this macro now that we're done writing it. Let's go to the definition, and you can see it calls something else. So it calls this define with these arguments, and this gets really messy. So we can have variable arguments, but you can see generally we pass in the node ID, the initialization function that needs to get called, the pointer to the device's power management resources, which we don't have any. That's why this is null, which you can see here. And then we have a pointer to the device's private mutable data. Once again, we don't need this. This is a simple button driver, but you could have private data in here as well, so we're just going to pass in null. And then we have the device's private constant data, which is basically our config information. That is the config instance number that we created here. That's part of this code generation. Next, we have the initialization level. You have before kernel, 1 and 2, or post kernel. This is fine being after kernel, so post kernel is good. Then we have the device's priority in its initialization level, and there's a bunch of macros you could use for this. We're just going to use this GPIO init priority. Notice the config underscore, which means this is a Kconfig property. Feel free to set this to whatever you want. I'm just pulling this right out of other samples that used this priority level. This is something you can set or change in Kconfig. And then finally, we have the API. This is a pointer to the device's API struct. You may not have any functions you want to call. This could just be a driver that holds data. But in our case, we want to be able to call some functions like getting that button state. We have the API functions here. We set that to one of the fields for that struct, and that whole struct gets passed in for this particular instance. Notice that this API is the same for all instances, which is part of the reason why we pass in the device into this function so we know which instance we're dealing with. So whenever you have one of these, say, public-facing functions, you often want to pass in that device information so you know which instance you're talking about. In this case, it's not the instance number, but rather the actual device, so I can get which button, or I guess which pin, we are talking about when we try to get the information by calling this pin get function. We are almost done. This is probably the trickiest part of writing driver code for Zephyr, is understanding how to work with this macro expansion or macro magic in order to create instances for your drivers. This is what allows us to have multiple instances of drivers if you want to have, say, multiple buttons or multiple I2C devices of the same type on the same bus, but with a slightly different address. We can use the same code to create instances of that API and data, much like you would in object-oriented programming, but we do it in C rather than, say, C++. And we need one more magical Zephyr macro, and that is this DT_inst for each status OK. The Devicetree build process, or Zephyr, calls this macro. It looks for this macro whenever you pass it in this driver code, as we defined up top with the DTDRV compat macro. So once the build process knows that this is a module, it's considered a driver, it looks for this macro or something similar. I'm sure there are others you can call. When it sees this, it's going to call the macro that's passed in as the argument. In this case, it's going to call button define, and it knows to pass button define an instance number. So for each instance in the device tree of this device that matches that compatible, in this case, custom, button, as long as the status for that node is set to OK, it will call this button define macro, and that's going to generate code for that particular instance. And it's going to pass in a generated instance number like 0, 1, 2, 3, and so on. Let's see if we can look at the definition of this. Sure enough, here it is. Feel free to start digging into these. They get complicated real fast. It is a lot of macro magic going on to say, hey, let's look for a particular compatible. Does it have the okay for the status? Basically is enabled. And then it keeps calling through that to unroll your macro here, the macro that you defined and passed to it, and it gives it an instance number that has been generated by the build system. With that, our driver code is done, but now we still need to create a module, bindings, Kconfig, and Devicetree information. So we're only part of the way done creating our driver, but the code is done. Let's start by creating our CMake lists to help the build system compile this code. So in our button folder, we're going to create a new file. We're going to create CMake lists. The first thing we're going to do in here is call this magical Zephyr library function. This declares the current directory, in this case driver/button, as a Zephyr library. We can give this function a name, and we can use it to name the library. But if no name is given, it defaults to the name of the directory, which is why you will see Zephyr using this function as is with no parameter or argument given, because it's just relying on the directory name. In this case, the library is known as button. That's why we have button in the drivers directory. And this is how you will see the Zephyr RTOS source code organized. You'll have a drivers directory with the number of drivers or subdirectories with drivers in them. In each of those, you will find CMake lists files that will declare each of the libraries. Next, we're going to list the source code files for this library. This is the C code. We're going to use this magical Zephyr function. I'm assuming that Zephyr on the back end somewhere defines a target for creating these libraries and then knows how to include those libraries when we are searching for code or wanting to link against them. If we want to be able to find this library from our source code, we need to call this Zephyr include directories. Once again, it just makes the header files in this directory, the button directory, accessible by our code, so we can include button.h. Let's save that, and this little dot's up here, so let's make sure we save our button.c driver code. Then in the drivers directory, let's create a new file. There we go, another CMake lists, because CMake loves the whole recursive thing within directories. Next, we're going to use this custom Zephyr function, this add subdirectory ifdef. It imports the button subdirectory only if the Kconfig option custom button is defined. This is how we can use Kconfig to enable or disable various software components. This is the magical command that does that. So if custom button is not defined and we try to include button.h, you will probably find that the build process fails. In fact, I think the linker fails because even though we've told Zephyr to build it, it won't link properly, or it might not just find it. No, I take that back. Actually, what happens is CMake goes through here during the build process and it essentially can't find the button subdirectory if custom button isn't defined in Kconfig, and so CMake just throws an error during the build process to say, I can't compile this because I don't know where this source code is. Let's save that, and I'm going to close these down. Then in our top level button module, I'm going to go ahead and create another CMake lists.txt because yay CMake and recursion through the directories. In this one, we're going to use the standard add subdirectory that CMake just goes into the subdirectory and looks for the next CMake lists.txt file. And we're going to also use this custom Zephyr function to add subdirectories to the compiler's include path. This is basically looking for .h files so that our application code can find them, include them, know which functions it can use, and then ultimately link to them once the build process happens. CMake is now set up, which helps Zephyr build and link to this particular driver. Next, we should do Kconfig so that we can turn this driver on and off in software. So back in our driver code subdirectory, let's go to button. We're going to create a new file. We're going to create Kconfig. Hopefully some of this is starting to make sense to you. As we went through each of these in earlier episodes, we looked at CMake, we looked at Kconfig, and then in a minute we'll look at Devicetree, and all these pieces come together to help you create your own device driver. As you saw in the C code and CMake lists files, we need to define our custom button Kconfig option. So we're going to define this symbol, custom button. We're going to declare it as a Boolean and give it the description of custom button. We're going to set the default to N, so turn it off by default. we're going to say that it depends on the GPIO driver that is defined elsewhere in Zephyr. That GPIO is a symbol in Kconfig. Feel free to look it up with like menu config. We're going to give it some help information. In this case, we're just going to say enable the custom button driver. This is very similar to how we created our own custom Kconfig options in the previous episodes. Let's save this. And like CMake, Kconfig also likes these recursive folder dives. So we need to make another file in drivers outside of that button directory, also called Kconfig, just like that. Just like we did in Kconfig, we're going to include the button subdirectory, but we don't include the directory. We actually have to include the specific Kconfig file in there. So we use this rsource function to do that, and we just tell it go look in the button directory for the Kconfig file. Let's save that, and I'll close out of here. And then one more, new file, Kconfig at that top level button module directory. So we have our CMake lists, that's the top level, and a Kconfig, that's also our top level. And just like before, we're going to say go look into the drivers directory and look for a Kconfig file there. And then that one's going to say go look into the button directory and look for the Kconfig file there, where it finally gets that new option information, this new symbol that it should put in menu config that we can enable or disable. All right, so Kconfig is now set up for our driver that allows us to turn it on and off. So we need to worry about the device tree stuff. So this is where we're going to define our custom device tree information that the user can then set up and help define information that then gets declared or instantiated in that driver code. So in our button, this is the top level module here. Let's create a new folder. We're going to do DTS. And all we really have to define here to allow for that device tree stuff to happen, that the user can set it, or the developer can set it, is to create our bindings file. We don't need to actually define custom device tree source stuff, but Zephyr puts bindings files in the DTS folder. So we'll create a bindings folder in there. In fact, if you go look at the Zephyr source code, you will go to DTS, you will see information for each of the common architectures, and then there's bindings. And this is where you can find all the bindings files for all the devices, even though their driver code is defined in the drivers folder. So we're just setting up our module to mimic what we found in the Zephyr source repository. In bindings, we could probably put button, let's see, so drivers, nope, we want to go to DTS to look at this source. Under bindings, if we want to mimic something like this, there's GPIO, but we're kind of on top of GPIO. I think the best way to do this is to create a folder to mimic this that's called input, because it looks like it has similar stuff here that built like GPIO keys. There we go. So it's built on top of underlying GPIO information. So that's why we would go into bindings. We're going to create our folder called input. I don't think that the name of this matters too much. It's just trying to organize it in a similar fashion as to what Zephyr does by convention. So under input, we're going to create a new file. And we're going to call this one custom, button.yaml. I'm pretty sure that we need to name the folders DTS and bindings, because that is where Zephyr is going to look for device tree information. But then how we organize it under bindings is kind of up to us, because I believe Zephyr goes through these folders recursively, looking for YAML files. And remember, the name of the YAML file doesn't matter. What matters is the compatible property that we're about to put in. So we're going to call this custom, button.yaml out of convention, but then we're going to define the bindings compatible so that Zephyr knows what to look for in the device tree when the developer configures that, and then matches that up to the correct compatible code that we defined in our button.c. Pretty sure this is optional, but let's give a description to our device. You'll see this all the time in the Zephyr bindings files. And here's the magical compatible property that we need to set. This string, custom, button, needs to match the one in our device tree source when we go to define that in our application, as well as the DTDRV compat macro in the driver source code. Remember that comma is going to get replaced by an underscore, so when we go to our button.c, it should match the one that is right here up top. And if I remember, that has to be up top before anything, because Zephyr looks for that before trying to compile anything after that in the code. So that's why you will see this as the first line before anything else, minus my comments. So down here, we're going to define our required properties. We're going to define a custom property called pin. That's going to be the name of it, and you saw that in our C code. This is going to be a p handle or property handle, and it will be required that the user fill this out in their overlay or DTS files. So if we come back to our button.c, come down to our macro expansion stuff, you will see that we're using the DTP handle in order to get that pin property. And we know that's going to be a p handle, and the Devicetree spec get will get that information and put it into this button struct for us. So that's where you see this pin. It is the symbol that matches what we are defining here. And that allows us to get the pin information, much like we did in episode 4, that we can then use to read the state of that pin. With that, our bindings file is done. That sets up an interface that lets the user know how to create custom Devicetree nodes in order to use this driver. The last thing we need to do for this driver is to declare it as a Zephyr module. We saw that in a previous episode. Otherwise, Zephyr won't know what to do with this folder. So if you remember from this say hello, we created this Zephyr subdirectory, that naming is important, and this module.yaml, also the naming is important. So let's close those down. In our button module, let's create a new folder. Zephyr looks for this folder called Zephyr. In here, we're going to create a new file. We're going to call it module.yaml, also naming important. We saw this previously. We're going to give the module a name called button, and we're going to tell Zephyr some information about where it can find the build source code. Specifically, we're going to say, hey, look in the current directory, which is one outside of Zephyr. So in the button directory, look for CMake lists.txt and follow the information in there, which just includes stuff from the drivers directory and so forth. It also sets up where to find the Kconfig information. It's going to look in one directory up. So in button, it's going to look for a file called Kconfig, which we set up previously. And then any optional settings. In this case, we're going to define the DTS root or the Devicetree source root. Also here, and this is why the naming of those directories is important, notice that we didn't specify the bindings file. We just said, hey, look in the button directory. So up one, that's here. Look in here for something called DTS. Zephyr looks for this exact naming, DTS. In here, it's going to look for something called bindings, also naming important. And then after that, it's going to go through anything it finds in the bindings folder recursively to look for these YAML files and find this compatible field in order to match it up with the driver code. So with that set up, we can save this file and our custom driver is written, which means we can now move on to writing the application code for it. If you are writing driver code to share with the world, you can take this and now share it, say, in a GitHub repo. You can give people information on how to include this as an out-of-tree module, as we are doing with this example. You could also, for example, include it in the Zephyr repo by forking their repo, putting your files in the appropriate subdirectories, and then doing a pull request to see if the Zephyr community approves it, and you will have your device driver as an official Zephyr driver. But for now, let's go ahead and write that application code because that's a very important step to test your code. Let's go ahead and shut these down. We're assuming our module is set up correctly. If not, we will come back and debug that. Let's go into our apps, create a new folder. We're going to call this 06 demo device. As we've done with all of our previous demos, let's go ahead and create a new folder called boards. We're going to put our overlay file in here for our particular board. We're going to call this ESP32S3 devkitc.overlay. We're going to create two aliases under the root node. We're going to call it mybutton1 and mybutton2 so that you can see how this instantiation process works so that multiple instances of the driver code, or at least of the driver config information, is created for each of these button instances. And that's why we have two buttons on our breadboard. We're going to create this custom node called custom buttons under the root node. I don't believe that the positioning or naming of this particular node matters. We just need a way to group our button nodes together. Under that, we're going to define our button 1. Note the label here, button_1, should match the button_1 that we gave to our first button in the aliases, so that needs to match. And then we're going to give this subnode some name. I'm going to call it custom_button_1. That naming doesn't particularly matter. And then in that subnode, now I'm going to list the compatible of custom comma button. That needs to match all of the compatibles that we've set in our driver code, and that's how Zephyr knows to match it up to our driver. Then I'm going to set the pin to a node label. And remember, pin here is a required property. In fact, let's go to our modules. We're going to bring up our custom button bindings file, and this is where we set pin. It needs to be a p handle. So this property handle is defined by this @ and we're going to give it this node label that we're going to define in a minute. Don't forget about your less than, greater than symbols that tell the Devicetree compiler that this is a property handle. Let's do the same thing, but for button2. I'm just going to copy paste. Let's change these to button2, and instead of D4, we're going to call it D5. These are labels that we are about to define. Now we're going to set up our GPIO keys. This is very similar to what we did in the demo button. So if we go to our boards under demo, we go under here, we see that we created this custom buttons node. Actually, I think this is defined in the board nodes for the reset button or button 0, and we're just going to add this button to it and then change the property for that here. So I'm going to change the name of this to GPIO keys. But you notice it uses the same compatible here. And that way we can avoid some conflicts. I'm going to set the debounce interval to 50 milliseconds. I will discover in a future episode, this actually does nothing. It's just a user property that can be read if you want to do debouncing. I looked into it and I found that this is not really handled, at least for ESP32, in the internal GPIO driver. So you can set this debounce interval, it just doesn't do anything. We are going to use polling mode to disable interrupts. We will look at interrupts in a future episode. Then we're going to define our subnode GPIO4. We're going to give it some arbitrary name, and we have to have that label D4 match the label for our pin property that we set in our custom button. The only thing we need to fill out here is set the property GPIOs to the p handle array so that Zephyr knows which GPIO driver instance we want to use. Remember, we have 0 or 1 in the ESP32. They control different sets of pins. Tell it the pin number and any flags. In this case, we want active low because the button is pressed and it's set to ground. And then we want to add that internal pull-up. If we go back to our 04 demo, we can see this is exactly how we set up a custom button or custom pin here. This was all previously covered when we looked at doing Devicetree stuff and how to work with those bindings files to define, in this case, a GPIO's property. This isn't custom property, this is something set by Zephyr to configure how a GPIO operates. And we're just basically taking that information and then wrapping it in our custom button Devicetree and using our custom wrapper driver. Let's do the same for D5. So all I'm going to do is copy and paste that. I'm going to change this information to D5 so that we can use pin 5. Let's save that. And our Devicetree should be set up and ready to go. So we can close that down. And then let's collapse that. We're back in 06 demo device driver. Let's create a new folder. We're going to call this src for source. And we're going to put main.c in here. As we've done before, let's include our standard input-output as well as the kernel information. We need both of those, especially if we want to, like, I don't know, print K to the screen. We will also include our custom button.h that we wrote earlier. That is the interface file for our driver. Notice that we're not giving it a absolute or even relative location. CMake is going to include that header as part of the search process, so it should know where to find this. We saw that in the CMake episode. We'll set up our custom sleep time as we usually do. In this case, we don't want it to sleep too long so that we can print button states to the screen fairly quickly. Then we're going to get the Devicetree information from our Devicetree that gets populated from our overlay file. We're going to use the DT alias so that we can say my button 1, get that Devicetree information, and it's going to fill out this device struct for us. Remember, device is a struct that's defined by Zephyr, and we're just using that in our driver code, even though a lot of the properties or fields in that are just void pointers. We're going to do the exact same thing for button 2. Next, we're going to define our main. In it, we'll have a return variable like we normally do, and we're going to have state 1 and state 2. That is the state for each of the buttons. Remember, we have to pass that in to that get function we defined. We didn't need to write devices ready. Because we are using the device, for lack of a better term, class, to define our button, we can rely on some of these pre-made functions for us, like device is ready. That means that the init function was called for each of the devices and that no errors were returned from that. That's going to all happen in the background during the initialization process, and all we need to do is just call this device is ready, pass in that struct, that device struct, and Zephyr will determine for us if the device has been configured correctly. We'll then use one of the button structs to get that API struct for us. Remember, we defined that, so button API struct is defined for us. We're going to get a pointer to that so that we can call functions. We only need to do it for one of the instances. Remember that, at least in our case, those functions were global or static, for lack of a better term. They're not unique to each of the instances of the button. So we just need to get one of the API structs. We can call functions from that, and we can pass the button device structs into those functions so that the function knows which device it's dealing with. We're going to have our good old super loop here that will just execute forever. The first thing we're going to do is call that get function that we assigned in our API struct. We're going to pass it in button1, so that's passing in that instance or that config information for button1 so that it knows which button we're talking about, and it's going to fill out the state1 variable for us. If that returns something less than 0, we know we have an error, and we'll just print that to the screen. We'll say continues so that the do while forever loop just keeps executing. I'm sure there's a better way to handle this error, but for our demo purposes, let's keep it simple. Let's go look at that code, because we didn't actually define a get function. So how are we able to call button API get when we never wrote something called get? If we go to our driver code into button and we go to our header file, you can see that we are creating this get function by defining it here. So we're creating this signature and we're saying a pointer to that function is a member of this button API. So in essence, we're actually creating our own API and mapping a public-facing function, get, to a private-facing function. In this case, it is button state get, and that mapping happens right here. So even though we said .get exists, it's a pointer to a function, and here is that function, and the signature or the required parameters match what was defined in this header file right here. So if we go to button.c, this is where that mapping happens. So we can just call .get from that API that we defined here, and that public-facing function name is actually mapped to this private function. You will see this used a lot in things like the sensor interface, where the sensor API requires very specific public-facing functions, and those get mapped to the individual driver private functions. So even though the different drivers have different names for their functions, you know that because it's a sensor, it has a common interface, and you know what the functions are in that interface, and you can just call those in your code, which kind of allows you to hot swap sensors. Just know that they're all going to operate a little bit differently. For example, if you have one temperature sensor, you might be able to swap it out for another and call the similar functions, but it also makes writing driver code easy as you know what that interface ultimately needs to be for something like a sensor in Zephyr. So let's go back to our main and keep writing our application code. And all we're going to do is copy and paste this because we want button state 2. So I'm just going to rename all of these to button 2, as that's what we set up here. And that's all we need to do and change that error code. So then we pull button 1 state and then we pull button 2 state. Once again, I'm sure there's a faster and easier way to do this if you're dealing with entire ports of pins, but this is just demonstrating how you might create a driver for a very simple thing like a button. Next, we're going to print those button states to the screen. So we'll see 00 or 01, depending on the state of those buttons. And we're going to sleep the processor for, what was it, like 50 milliseconds, something fast so we can see the stuff being printed to the screen. And we will return 0 as Zephyr likes to have, even if we never get there. Let's save this. Our application code is done, but we still need to set up some information on how to build this. So we'll create a new file, and as we have done before, we're going to make our CMake lists.txt. We're going to specify the minimum CMake version, 3.20, to match what Zephyr has. As we've seen before, we're going to set the Zephyr extra modules variable and have it point to the modules/button driver. And that's giving it a relative location so Zephyr knows where to find that before we instantiate the whole Zephyr extensions within CMake. And that's what we'll do on the next line where we say find package. We'll say Zephyr and where to find it. In this case, we're going to rely on the environment variable that's been set. That is Zephyr base. We'll give the project a name, in this case, custom button, doesn't really matter here. And we'll tell Zephyr where to find our main.c and add it to the app target that's been defined for us. Let's save that. There's one final piece that we need, and that is prj.conf. As we saw in the Kconfig episode, we did define our own custom Kconfig symbol. Feel free to fire up menu config and go find it, or you can just trust me that it's there. And to make this simple, I'm just going to go into prj.conf. So for all of the projects that are using this, we are going to say custom button equals yes. We are turning that symbol on so that Zephyr knows to build and link to that button driver. Remember that we said only include these subdirectories if this symbol is set, and we are setting it right here. By default, the logging system is disabled, so we're just going to say log equals y, and then we need to define the log default value that essentially sets the logging level for us. In the Zephyr docs, you can find the possible levels for this. 0 is off, don't write anything, and then we have the different levels, and remember that if you set it to 3, that means also print out 0, 1, 2 in addition to 3, but don't print out anything 4. So if we set it to 4, which is our debug level, which we have some log debugging in our driver code, go ahead and basically print everything. So the default is set to 3, but we're going to up it to debug so you can see some of the messages we wrote in our driver code. Okay, let's go back to our prj.conf. We are setting that to 4, which is the debug level. Go ahead and save this. Note that in some systems, you might have to enable the GPIO explicitly, but I believe it is enabled by default for most of the board, so I'm going to leave it off. If we run into problems, we know we can come back and add that. I haven't needed to add that for any of the previous demos, so we should be good. Just keep in mind if you run into issues, if you see something about GPIO not being configured, because it's a dependency for our custom button, you might run into issues there. But it should be enabled by default. With that, we are ready to build. So let's bring up a terminal. Let's go into Workspace. Let's go into Apps, and we're going to go into 06 Demo Device Driver. Let's go ahead and build this project. We'll see what happens. And looks like I did get a failure here, so let's figure this out. So it says invalid board, and that means I did not define my board correctly. So let's go back, and I think I need to be S3. Let's try that again. Before we flash it and see if it works, let's go to our build directory. Under Zephyr, we can go to Kconfig. Our symbol should be in here called custom button. There it is enabled here. And you'll notice that Zephyr adds this custom symbol, as we saw in the previous episode. What we really want to look at is this DTS, because this tells us if we set all of this up correctly. So here's our aliases. Here's the 2 properties that we added, and we're looking for custom buttons. So under the root node, you'll see that there was this buttons node. In the previous episode, we just added a custom button here to avoid conflict with that and to demonstrate that, yes, you can just arbitrarily add nodes to this as long as you know how to access the information in them and as long as you're using the correct compatibles. It mostly just works. So we're adding under the root node this custom buttons that we just defined for ourselves. It's pretty arbitrary. And we're defining button 1 and button 2. These are using the pins D4 and D5. These are p-handle properties. And in our GPIO keys that we defined over here, once again, we are not conflicting with anything that was created in these buttons. They're just 2 different nodes that just contain similar information. In fact, this can continue to use its interrupt mode if it wants, and the pins here can use their polling mode. We can also set the debounce interval, but that doesn't do much in my experience. And we're going to set up the GPIOs here. Notice that the Devicetree compiler gives us p-handle numbers, because that is what's used to identify the actual handles here and here, rather than using something like a name. It actually gives it a number, and when it wants to access that information, it goes by that p-handle number. So that's something you should never touch and never use this property, because it's something that the Devicetree compiler handles for us. So with that, let's bring up our shell. Let me make this a little bigger so you can see I'm in the directory already. And we're going to call the ESP tool to flash the binary that we created to port 7. We'll set all of the other parameters that we've done before, like having it auto-detect the chip, setting the baud rate, resetting before and after, actually writing the flash, setting it to address 0, and then ultimately passing in the binary that we just compiled. So let's go ahead and flash that. With any luck, that should flash. Feel free to use the serial terminal of your choice. The Python one is pretty universal across operating systems, assuming you have Python installed and the PySerial package installed. Let's open that up. And we can see our debugging information coming through because we enabled debug logging. And you see our button states 0 and 0. I'm going to push one of the buttons. So that goes to 1. I'm going to push the other button. That also goes to 1. I'm going to push both buttons and they both go to 1. So now you can see how this driver is working for us and how to write a simple application for it. Let me restart that. So I'm going to restart this. Oops, I do need to push the restart button on my ESP32. And then I'm going to stop that serial and let's scroll up to this initialization. You can find our debug information that is here. So this is the logging that we put out during the initialization. You'll notice that it happens before our main function is called because we told Zephyr to run that function during the initialization. And you can see that initialization happening here while it's initializing things like memory, the threads, any other devices you might have before kicking off your actual application code. In this case, we have it print out instance ID numbers, which are 0 and 1. So if we go back to our code that we wrote for our driver, let's collapse all of these. Let's find our driver code. These are the numbers that are getting passed to this macro, instance number 0 and instance number 1. It's actually generating code that's button config 0 and button config 1 that creates different structs for each of the buttons. It also means in our initialization code, because we added ID as one of the config options, remember that gets passed in, where is it, right here. So in that particular instance config, we capture that ID number so that we can print it out. You don't need to do this, it's just useful to see how this is happening. And this is where we log to the console and we say print the ID of that number that we get from our config. I know this was a lot of information. I am going to give you a challenge, and that is to create an I2C driver for the MCP9808. It's a relatively inexpensive temperature sensor that you can get breakout boards for. You should have the module match what you did for the button module, and you are totally welcome to use things like ChatGPT if it gives you anything remotely accurate. It kind of works for me when I'm asking it about Zephyr stuff. You are welcome to go into drivers. Take a look at what Zephyr has done with that JEDEC driver. So if we go to sensor, you go down to JEDEC, and it actually has code in here. So you're welcome to look at this. Note that you don't need to include all of this because this has things like triggering on interrupts, which you don't need to worry about. Just get it to simply read the temperature from that device. If you really want some help, I have a tutorial at github.com/SeanHemel/workshop Zephyr device driver. This walks you through the process of creating that device driver and creating an application for it. So feel free to work through this, but your job is to get that I2C driver so that you can understand how to create your own drivers and get some practice doing that because it can be fairly complicated. When you're done, if you flash the application to your board, you should have it printing out the temperature to your console as I've done here. So temperature is 22.875 degrees Celsius. I am printing out the debugging information like we did in the button example. So that's what all of this is. Oh, by the way, if you see this like EC weird symbol, that's coloring information. So if your terminal supports it, it will pick up this information and color these lines in a certain way. But because this PySerial mini term is really simple, it doesn't do it. It just prints the raw characters for us. So if you're curious what that is, you can just ignore it or use a better terminal if you so desire. But good luck with this challenge. I know there's a lot going on in these device drivers. This is the culmination of the past few episodes as we look at the various tools that make up the core of Zephyr. Take your time with the challenge and feel free to come back to these episodes if you need to refresh your knowledge. Next, I'll go over the basics of connecting GDB to OpenOCD so you can do step-through debugging in Zephyr and VS Code. Happy hacking!